Hello, physics friends. A common point of confusion in relativity is the distinction between measuring versus seeing. So throughout the relativity part of this class, we're going to talk about kind of the bizarre consequences of special relativity, in particular the fact that clocks that are moving are not in sync with each other, the fact that a moving clock ticks slower than a clock that's stationary, and also the fact that moving objects are shorter than the same object if it were at rest. It is often the case that students and first-time learners of relativity think that these are somehow consequences of the time it takes for light to travel from that object to their eye. And so they think it's an effect that has to do with seeing an object. And the point of this video is to make a distinction between measuring and seeing. And in fact, all of those consequences that we just described are not due to light travel time. It's not because it takes light some amount of time to travel from A to B. That is a true statement, that it does take light time to travel from A to B, but the effects that we're talking about, the time dilation and length contraction, and the fact that the rear clock reads different than the front clock, those are all due to other reasons than the light travel time. So here we're just going to talk about this distinction between measuring and seeing. So we'll start with seeing, okay? So let's say that we're standing on Earth and we're looking at light that's coming from the sun. So here we have us on Earth, and this red dot is the photon coming from the sun to us. Well, one way to talk about the distance between the Earth and the sun is to say that it's about 8 light minutes away. 8 light minutes away means it takes about 8 minutes for something traveling at the speed of light to go from the sun to the Earth. And the photon is traveling at the speed of light. So it takes the photon about 8 minutes to travel from the sun to our eye on Earth. And what that means is when we look at a picture of the sun, we are seeing the sun as it was 8 minutes ago. In order to see the sun as it is now, we have to wait 8 more minutes for the light that's emitted by the sun right now to eventually make it to our eye. So it's in this sense that we have a delay between an object and our perception of the object. And we talk about that delay as seeing the object. And in order to recognize that there's a time delay associated with that, we'll reserve the word seeing for this kind of process where we have to account for the travel time of light from the object to our eye. In particular, let's say that it's noon on the sun when this photon was emitted. So the picture, say that this photon and maybe a bunch of photons emitted at the same time are carrying with it, is a picture of the clock reading noon. Okay, so 8 minutes later, that light will reach our eye, and the picture encoded in that light will say noon, even though 8 minutes has elapsed on the clock that's on the sun. So although we're reading a clock that says the clock reading that we're receiving is saying noon, at the instant that we receive that message, the sun's clock is actually reading 8 minutes past noon, because 8 minutes have elapsed in the time it takes the light to travel from the sun to the Earth. In contrast, we're going to reserve the word measure for something slightly different. For the measurement, we're going to assume that the person making the measurement is able to correct for the light travel time to understand something about the actual time the light was emitted or the actual length of an object. In order to do that, we have to assume that the observer has some technology. They have to be able to make measurements of time and make measurements of length. And we can assume that there's basically a grid of throughout space of clocks and rods that allow this person to make those measurements. And that's not far-fetched, right? If you're going to do an experiment, you can put in place techniques to make those kinds of measurements. So in our class, we're going to use a little diamond symbol as a symbol for a clock, okay? So I'm going to draw here a diamond, which represents a clock on the Earth, and a diamond, which represents a clock measuring time at the location of the sun. And I'll put those diamonds in all 4 of these positions. Right? The first diagram at the top of the page here is showing the instant of time that the photon is leaving the sun, and the second is showing the instant of time that the photon reaches the Earth. Okay, and we know something about the time. Let's say that we launch that photon at noon. Okay, so in that case, the reading on this clock would be 12 noon and no minutes. And the same would be true for the clock on Earth, because these two clocks are at rest relative to each other. We're going to learn later in the course that if the clocks are moving, then they have different readings. But if two clocks are at rest relative to each other in this frame of reference, their readings will be the same. Okay, so then what will the readings be in the second diagram? Well, we know that it takes 8 minutes for light to make the journey. So the reading on the clocks in this second diagram has to be 8 minutes later than the reading when the photon was launched. So these readings will both be 12:08, 8 minutes after noon. Okay, so how do we talk about the measurement that this person on Earth is making? Well, we're going to say that he or she is receiving a photon at 12:08 their time, but they are aware, because they've made measurements in some other way, that the distance from the Earth to the sun is 8 light minutes. Okay, and so they get a measurement of 12:08, but they have to correct for it by subtracting off 8 minutes, and they can therefore say that I measured the arrival of the photon at 12:08. I know the sun is 8 light minutes away, therefore I measure that the photon left the sun not at 12:08, but at 12 on the nose. So this is the distinction between measuring and seeing. And the key point is that everything we're going to do in relativity is really focused on these measurements. And all of the quote-unquote bizarre consequences of relativity are not due to the finite speed of light, meaning that it takes time for light to go from point A to point B. Even when you correct for that, we still are going to end up with these bizarre outcomes of time dilation, length contraction, and the difference between clocks readings when they're in motion.